Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer architecture. We have been looking at various subsystems of the computer system in a fair amount of detail. So, we have covered the CPU, we have covered the ALU and other details within that. We have looked at IO systems, we have looked at memory systems in a fair amount of detail. So, what we will look at in today's topic is that we will look at some of the trends that have come up these days, which is basically the multi-core processors, and then of course we will try to put everything together. So, whenever we talk of trends and we talk of the development that is there in architecture, we always talk about something called Moore's law. Now, no talk on architecture is ever complete without mentioning something called Moore's law. Now, Moore's law basically it was something which was a law which was predicted by Moore, Gordon Moore, who was one of the founders of Intel. So, he came up with this conjecture that the number of transistors per chip doubles every 1.5 years, okay? And this is something that has contributed to the overall improvement in performance of systems as a whole over the last 30-40 years. Okay? So, you can see that from 1970 when the first 4004 Intel processor was introduced, which is just a few thousand gates, 1000 transistors, from there up to 2005 itself we were hitting somewhere at about 1 billion transistors. Okay. So, this is something which has generally contributed to the improvement in performance. So, how is this trend really sustained after 2000? That is where we see a difference. Okay. So, in fact, what we see is if you look at performance of systems overall starting from 1978 to 2012, if you look at, it is increased by about 25,000 times. Okay. Again, when you look at performance at 1978, if you consider that as 1 when compared to a VAX 11780 machine, it is 25,000 times that when you are looking at Intel Xeon processors, which were even around 2010-2011 time frame. So, now we have even faster machines. Okay. And if you look at what has contributed to the increase, one is of course the larger number of transistors that we have, and the second thing that we also see is the clock rate has been increasing steadily. We talked about 5 megahertz as the clock rate in 1978, whereas now if you look at 2003-2004, clock rates came to about 3200 megahertz, that is 3.2 gigahertz. But from that time frame you can see that there is not any significant increase or improvement in the clock frequency. Clock frequency has been around that range 3.2, 3.3, 3 gigahertz, that is the range at which the clock frequency has been. So, there is a reason for why the clock frequency really hasn't increased beyond a certain level. The reason for that is that the power consumption that we have, power dissipation that happens when you have higher frequencies is very high. Okay. So, what we say is that we have reached certain limits, we have reached what is called as a frequency wall. So, what do you mean by frequency wall? That it is not really crossed 4 gigahertz in the last few years, and the reason for that is that we have hit what is called as a power wall. What is a power wall? That the amount of power dissipated, that is the dynamic and static power dissipated, becomes so high when you reach these kind of frequencies that your chip can almost burn out. Okay. There is, when you say there is so much of power dissipated, it also means that there will be a lot of heat dissipation, and there can be so much heat that the chip can actually burn out. Okay. So, we are hitting what is called as a power wall or a thermal wall. And of course, there are other limits that we see, which is with respect to the ILP, which is instruction level parallelism. There is only so much amount of ILP that is there. So, you can't go really much faster with these kind of devices. And then of course, there is a memory wall and there are certain manufacturing costs that are involved. Okay. But what we are mainly concerned with is this power wall, and we can see that how this is something which has led towards multi-core processors. Okay. So, if you look at power trends, okay, what has happened with respect to the amount of power consumption that or the power dissipation that has been happening in these processors from 1970s to 2000, if you look at what is happening, what has happened, we were at 4004 Intel processor was consuming somewhere less than a watt of power, 0.3 watts or so on, whereas P6 Pentium, P6 and so on, we are in the range of 10 to 100 watts, okay, that is the kind of range. When you talk of power, there are two components, one is static power and another called as dynamic power. So what we mean by dynamic power is the power per transistor that you have, which also varies with respect to the frequency. That is, when you turn on and turn off devices, there is some power consumption that happens over there, which we call as the dynamic power. Now dynamic power, you can see, is proportional to these three components. It's actually equal to capacitance into square of the voltage into frequency. So you can see that if I increase F, therefore in this equation, power will increase. So increasing frequency increases dynamic power. Similarly, increasing voltage will increase dynamic power, which is why we keep lowering the voltage. We have a lower V, okay, and therefore that will help us to lower the power. But what is also important is, it is not just power per transistor, it is the power per area, that is the power density, which becomes the problem. Remember, we are having now more number of transistors per area as per Moore's law, because the semiconductor technology has been improving in that direction. We are able to put more number of transistors per unit area. So what happens is that it is not just power per transistor, but power per unit area that becomes important, which is called as the power density. So let us understand what happens with respect to power density. So if you look at power density, that is watts per square centimeter, has been pretty much at this rate, at about 10 watts per square centimeter up to about P6. Now there itself, at that rate itself, you are pretty much close to what we have in terms of a hot plate. Okay, a hot plate has this kind of a power density. If we go a little further, okay, if you go to 100 watts per square centimeter, we will be reaching the power density of a nuclear reactor. Okay. If you go a little more than that, if you start moving towards 1000 or even 500, 600 watts per square centimeter, you will reach that of a rocket nozzle, and if you hit 10,000 watts per square centimeter, you will hit that of the sun's surface. Okay. So that is the kind of power densities that we are talking about. So obviously we can't go beyond a particular range, so we have to keep the power densities low. You can see that that's the reason why there is a lot of cooling that is there in most of our devices. There is a fan which is mounted right on top of your processor. Okay. And if we start going at these levels, you will find, especially when you have huge data centers which are constructed with large number of processors, the cost of cooling can be higher than the cost of the processing itself. Okay. So which is why it is very important to take a look at these kind of power trends than the heat dissipation trends and so on. So what is it that we want to do? We want to have a good performance, but at low power. So we are now talking about a power performance ratio. Let us look at what are the terms which affect performance and which are the ones which affect power. Now performance, we know, is can be measured using execution time, which is what we want to keep low. Execution time has to be low. Execution time, we know, is IC, instruction count, into clock cycles per instruction divided by the frequency. Power, on the other hand, we know, is C into V squared into frequency. So look at what will happen here. If I increase frequency, my execution time will come down, which is desirable to improve performance. If I increase frequency, my power will go up, which is not desirable. Okay. So frequency is something that we really need to understand correctly and play with correctly in order to get power performance correctly. Okay. So what we want to do, therefore, is you want to decrease the frequency, and therefore so that you can decrease the power, but you want to increase performance. So how do we do this? So it is in this situation that multi-core processors have come up as a solution. Okay. So what do we do with multi-cores? So what we do is we use additional cores, that is, we have more transistors now. Okay. So more transistors obviously means that I can have, instead of having one single core with a large number of transistors, we have two cores. We have large number of transistors, so split it into two, have two cores. The two cores work at the same, I can work at a lower frequency, but because I have two cores, I can increase my performance by 2 times. Okay. But since I have decreased the frequency, I can get the same performance at about 1/4 the power. Okay. That is the idea that is used. So one of the benefits of this is that if you keep the cores simple or smaller, you get more predictable performance, and you can get overall much better performance for the same power that is consumed. Okay. So same power budget, but we are trying to get better performance. Of course, we have more number of transistors, which is why we are able to put more number of cores. Number of transistors is increasing, but when the number of transistors increase, we do not look at that as one single processor, but we look at that as multiple processors sitting on a single chip, running at lower frequency so that the power consumption is not high, but since we have more number of processors, we get better performance. That is the idea that is used in multi-cores, and this is what we see as a major switch that has taken place with respect to multi-core, with respect to all processor manufacturers. Okay. So in fact, sometime around 2005 Intel made the switch and they said we are dedicating all of our future product development to multi-core designs. So, this is a sea change in computing. So, this was something which was started in 2005 by Intel, and almost all other microprocessor companies have switched to multi-cores. So, now we talk about dual core, quad core, 8 core and so on. In fact, if we look at, there are also what are called as many core systems now. The graphics processors that we have today, the latest NVIDIA graphics processing unit that you look at, they have hundreds of cores. We talk about something like 440 plus cores. Okay. We have a Tesla 20 series, then you have different architectures that are there as part of the NVIDIA cores. There we talk about hundreds of cores. So, that is the kind of trend that we are seeing today. Okay. So, if you look at inside these multi-cores, okay, now that we have these multiple processors put together, how is it that we are actually able to get the performance out of them, and what are the additional issues that we need to consider when we start looking at these multi-cores. So, that is something that we need to understand. We will just take a brief look at some of what happens inside multi-cores. So, if you look at what is there inside multi-cores, what we are essentially been doing is we have borrowed some architectures from the parallel world. Before multi-cores came into the picture, we knew how to construct parallel processors, okay, using different parallel computers. How is it that we can get better performance? That was something that we knew. Only thing now is that all those parallel processors are now there on a single chip, on a single die itself. Instead of being on multiple processors, multiple chips, all of them are on a single die. So, same ideas that are used for parallel architectures can now be used on multi-core processors. So, we use what are called as shared memory models, both centralized shared memory models and distributed shared memory models, where we talk about something called uniform memory access models or non-uniform memory access models and so on. And then we talk about different interconnection networks. So, the interconnection networks are required to connect up these devices together. And then how is it that we make use of different types of parallelism, data level parallelism or thread level parallelism, what kind of parallelism is used, okay, and how is it that we are able to get performance out of it. So, that is where the focus currently is in terms of understanding architectures and developing architectures. So, a little bit on shared memory to understand what we mean by this. This is because it is one of the most commonly used techniques that is used for multiprocessors and multi-core processors these days. What we mean when we talk about a shared memory multiprocessor is that all the different processors share a single physical address space. Okay, it's one common address space that is used by all the processors. So, there is a common memory which can be used by all of them, it's a shared memory, and of course, all of them will have some cache that is there which is local to each processor. The reason why we will have separate cache for each processor is that you will reduce contention to main memory, and main memory we know is always slow. So, performance can be improved if we have the local caches. Okay. And any synchronization which is required when you have different processes working on some shared data, that will have to be done by means of some locks and some synchronization mechanisms. Okay. So, some synchronization mechanisms will be provided as part of the architecture space itself, okay, and we have a shared memory space that is used. Okay. Now, write programs which will run on these different processes, interact with one another and solve a large problem. That is how we do with shared memory. Multi-programming is what is done these days. Okay. Another mechanism that is used is a message passing mechanism. Here this is typically done when we have processors which have their own private physical address space. So, you have a processor cache in its own memory. So, different such processes connected by means of an interconnection network, and whenever you want to share some information between the processors, it is done by means of messages. So, messages are sent between the different processors. We have different address spaces for these. So, information can be sent only by means of certain specific messages. Messages are understood by the processors, and using that they will be able to communicate with each other to solve a large problem. Okay. So, these are the different types of techniques that are used when we have multiprocessors. We will take a short break now and then come back and continue with the rest of the content. Welcome back after the break. So, we were just looking at the different schemes that are used in multi-core processors. We looked at shared memory processing and message passing that is used for talking for different processors to talk to one another. Okay. Now, when we talk of these different multi-core processors, there are certain classifications and certain terms that are used to understand these processors. One such classification is by Flynn. It is called as the Flynn's classification scheme, which is basically used for parallel process systems or multi-processor systems, and the same thing can be used for multi-core processors as well. So, here we talk about whether we use parallel data streams or parallel instruction streams. So, depending on whether you have a single instruction stream or multiple instruction stream, and similarly single data stream and multiple data stream, there are 4 classifications that we look at. One is SISD, which is single instruction, single data stream. This was our original initial process, all fell into this kind of a category, the single core or single instruction stream processors. Then you have single instruction, multiple data stream processors. So here your extensions to the Intel processor which could take care of multimedia instructions, where a single instruction would actually operate on multiple data simultaneously. This comes under this category of SIMD processors, SIMD or single instruction multiple data processors. MISD, multiple instruction single data, we really do not have any examples of that working today. So, it is more for the classification completeness that we could talk about that. The other is multiple instruction multiple data. So, here we are talking about parallel programs running on different set of data. Okay. So, all our multi-core processors, typically the Intel multi-core processors, they come under this MIMD kind of a scheme. So, this is one classification scheme that one should generally be aware of. Okay. Now, we will look at some examples of different multi-core processors that are that have been designed today. So, here we are looking at 2 quad-core Intel Xeon processor. So, what we have here is there are 4 cores over here, which is why it is a quad-core processor. But they are kind of organized in such a manner that there are 2 cores sharing one L2 cache, another 2 cores sharing another L2 cache, and these 2 are connected by means of a front side bus to a chipset through the 2 actual memory outside. So, these DIMMs here are memory devices. So, like this we have 2 such quad cores, which is why it is a 2 cross quad core Intel Xeon processor. So, these 2, so you can see that you have altogether about 8 cores together, okay, which can work to give you really good performance. This is an example of a 2 quad core AMD Opteron processor. So, here you can see that it is a slightly different architecture that is used. You have 4 cores to 4 Opteron devices, cores, each having its own cache, okay, a victim cache and then a shared cache, which are connected by means of a crossbar to memory controllers and through that to a DIMM. So, now when we connect up 2 such quad cores, these you can see are connected by means of a special hyper transport kind of a connection, okay, and a special interconnection network that is used over here. So, these 2 now can talk to each other. So, altogether we have about 8 cores. So, you can see that there are different ways, okay, you can see here the Intel quad core is organized in a different manner. Here you have these 8 cores organized in a different manner in the AMD process. So, like that you can see that there are different architectures that are used when you actually want to connect up these different processes, and of course, there are performance differences, improvements on one side and certain issues on the other side that we need to understand when we look at these multi-core processors. Okay. Another example is the IBM power process. We have the power 4, 5, 6, 7, 8 kind of process which are used today, which again you have different architectures which are used on these power processors. Another category of processors is the Sun's Niagara processor, Sun's T1 processor. Here what we have is we have 8 cores and all the 8 cores are connected by means of a crossbar switch to L2 cache which is shared. There are some L1 cache which is kind of there on each of the cores, which is private to each core, and then by means of a crossbar interconnect network they are connected to the L2 cache, and then from the L2 cache of course you have an external control to the DRAM controller which will connect to DRAM memory which is outside. So, with this, what is interesting about the Sun's architecture is that this is designed to be a multi-threaded processor with each core supporting 4 threads. So, you have 8 cores and 4 threads per core, which means 32 different threads can be supported on this particular Niagara processor. Okay, these are other details that you can always look up when you look up on these kind of devices. This is a 2 octa-core Sun Ultra Spark put together, which is called as a Niagara 2 processor. So, here what we have is whatever we saw right now, right, the crossbar switch and the 8 core system that we have, you can have 2 such systems connected together, okay, and then together they will give you much higher performance. Okay, this is some of the Sun related processors that we see. Okay. This is another example of an IBM's multi-core processor which is called as a Cell Broadband Engine, which was originally designed for some high speed graphics or gaming applications. So, what is interesting here is you can see that there are actually, it is called as a heterogeneous architecture in the sense that you have 2 different types of cores. So, what we have here actually is there are 2 cores, one called a power processing element PPE and another called an SP, which is a synergistic processing element. Okay. So, let me come back to this figure, you can understand it from this figure here. So, we have one power processing element PPE here, which is basically a power PC. Okay. This acts as a master processor or as a control processor, and then you have these different 8 blocks over here. These 8 blocks are the synergistic processing elements which will actually do a lot of graphic related processing or multimedia related processing. So, multimedia processing gets done in these 8 different cores. So, altogether there are 9 cores connected by means of a interconnect bus which is called the EIB. You have a special interconnection over here. So, now this PPE will control these different SPEs to do different processing in parallel, okay, and then achieve overall good performance. So, that is how the cell broadband engine has been designed. It was designed specifically for doing gaming applications. So, performance was one of the major factors here. So, you will see that inside each of these processing elements there are a lot of interesting techniques used to improve performance. This is again 2 of such IBM cell process being put together. So, you can actually come up with a 2 octa-core IBM cell processor. Okay, again you can see that you can get much higher data rates and performance with this kind of a system. Okay. Another improvement that we have been seeing with respect to multi-core processors and this thing is of course with respect to graphics processors and graphics, how graphics processing is done and how different processors have been designed for doing graphics. And we all know that the trend these days is in terms of much higher performance with respect to graphics systems, with the kind of graphics cards that we use and the kind of games that we all play with very high quality graphics. So, how is it that this kind of graphics quality has been achieved? So, we will just take a brief look at that. So, if you look at older systems, the graphics in the system was handled basically like this. You have your CPU, main memory, north bridge, south bridge and the different devices, and then there will be something called a nice VGA controller, okay, which will take care of doing the VGA display. So, all the graphics that we wanted, okay, was basically handled by this VGA controller. So, this is how the systems were earlier. Okay. From there what we have moved to is that the VGA controller instead has been replaced by what is called as a special unit called the graphics processor unit, okay, and so which is directly connected to this north bridge, okay, and this GPU is connected to a special memory called the GPU memory. So, GPU now takes care of all the responsibility, all the actions functions which are required for doing the display in an effective manner. So, this becomes almost a full-fledged processor in itself, executing instructions which will take care of doing all the functions required for our graphic for our high quality graphics display. Okay, this is something that we have seen. A variation of this kind of an architecture is what we see in AMD's processor, that is when we have an AMD kind of a processor, the CPU core and the north bridge come together as one single device, and then there is a chipset through which a GPU is connected, which is connected to the display. Okay, so, this is the kind of thing that we are seeing these days. Okay. But what exactly is there inside this GPU, inside this graphics processor? If you look at that, okay, this is the kind of thing that we are talking about. Okay, this is an example of the NVIDIA Tesla processor. So, what we have here is 1, 2, 3, 4, 5, 6, 7. There are some 7 such streaming processors. Okay, streaming multiprocessors that we talk about. So, each of this you can look at as a larger core within which there are some smaller cores. So, what we have is the smaller cores is within each streaming multiprocessor that we have, there are 8 streaming processors, and if you have you can see that there are 1, 2, 3, 4, there are about 15 to 16 SMs that are present over here. Each SM streaming multiprocessor having about 8 streaming processors. So, 16 into 8 you will get about 128 such small cores. So, if you have 128 such small cores, each core is capable of doing a lot of graphics processing. So, with such large number of graphics small core processors, you can construct these large GPUs and excellent processing capability in a single GPU. Okay. So, this is basically how the GPUs are being designed today. Small cores which can do very specific processing. Okay. In fact, they can do some floating point operation and some integer operation. So, many of these small cores put together to form a very large multiprocessor system. Okay. So, that is the kind of idea that is used in these kind of graphics processors. Okay. So, when we talk of these kind of cores here, we talk about many core systems, because we talk about hundreds of cores, 400 cores, 500 cores, 1200 cores and so on. So, that is the kind of development that we are seeing today. And what is very interesting about these GPU architectures is that they are designed mainly for data parallel systems. Okay. So, whenever we have any data parallel system, we can also use it for those kind of applications. So, a GPU which was originally designed for doing only graphics processing applications now can be used for other applications as well, provided those applications have a lot of data that can be processed in parallel. So, if you are able to identify data parallel applications, what we are doing these days is we are using these GPUs to perform the other tasks as well. So, now we are moving towards what are called as GPUs, general purpose graphics processing units. Okay, that is the kind of thing that we are moving to. Okay. So, if you look at the trend towards general purpose GPUs, we see that we are moving more towards heterogeneous systems, okay, CPU GPU systems. Okay, that is the kind of thing that we use. So, CPU will be used for sequential code and the GPU will be used for parallel code. And of course, there are some very specific programming languages and APIs that have been designed for programming these kind of GPU architectures. Okay, DirectX, OpenGL, and then we have something called Compute Unified Device Architecture CUDA, which is by NVIDIA, which is meant for GPU programming. Then we have OpenCL, which is used for, it is an open standard which is used for programming these GPU devices and so on. Okay. So, now that we have all this hardware, okay, which is there, what about the performance with multi-core processors? What we find is the performance has basically shifted from hardware to software. Okay. So, we say in general that the free lunch for software is over. Earlier we really did not have anything to do with improving performance by improving our software performance. We ran the same programs on a faster processor and we got better performance. That is not the situation now. Now the situation is that we need parallel software to exploit the power of these multi-core processors. So, in fact, now we find that there is a lot of shift towards writing parallel software and understanding these multi-core processes and exploiting the capability of these kind of processors. So, that is what we have today. So, that is the trend that we pretty much have, okay, that we have come to these days. So, to sum up, let me just quickly talk about the different things that we have looked at in the course as such. So, we have looked at, in fact, this picture here, if we look at, will give us the various things that we have covered. We have looked at what goes inside a processor. Okay, we have looked at ALU, we have looked at control unit, we have looked at pipelining, we have looked at various things inside a processor. Then we have looked at how memory is organized, right. We have looked at main memory, we have looked at cache, different cache schemes, those things we have looked at. We have looked at different peripheral devices, we have looked at I/O, how I/O is handled, interrupt mechanisms, DMA mechanisms and different types of devices that are used. Okay. We have looked at the controllers which are used to connect up these devices together, and we looked at bus standards which are used to connect various systems, various components which are there in a system together. Okay. So, all this put together is what we understand when we talk about computer architecture, and what we have looked at in these 30-40 lectures is that we have looked at the essentials of understanding the various components of a system. We have also looked at the current trends. So, that should give you some pointers to look at what you must be looking at in future. So, you need to do a lot of reading on some of these trends and understand how the architecture field is expanding and is moving in the current decade. Okay. So, to summarize, therefore, what we have looked at in today's lecture are the following. We looked at the multi-core trend, why multi-core processes have come into place. We have looked at some examples of multi-core systems, we looked at shared memory systems and so on. We looked at some GPU architectures and we tried to put it all together. Questions to look at today's content. Question number 1, why has the processor industry moved to multi-core? Question number 2, list the categories of systems as per Flynn's classification. Question number 3, which model does a graphics processor fall into? Question number 4, list 10 latest multi-core processors from 4 different vendors. You need to do a little bit of checking on the net to answer that last question. Anyway, hope you enjoyed the series of lectures. Thank you.